All right, let's get started. Welcome to discussion. Last time we were sort of like interrupted by the fire alarm, so we'll be continuing from where we last left off. We still have just a little bit to see in how to exec, fork, and use programs that way. How many of you have already started on the shell program? Okay, looks almost like everyone. How many people are done with it? Okay, not bad. All right, so in case you're still stuck on some things, hopefully today will help you out. After this, we will look at the XV6 code and we'll be looking at the scheduler stuff. Okay, so let's get to it. So if you remember the code that we had previously, we printed before. We then used fork to create a child, and if you are inside the child, we print that the child is printing, and then we actually use execvp in order to run ls within the child. Hopefully, everyone still remembers all the stuff from last time. So what we were sort of exploring before the fire alarm went off was this stuff. So let me show you. So here you see that the output from the child is being printed out to standard output, right? What we would like to do is we want to redirect this output to some other file or other pipes. So to understand how to do this, you need to understand one sort of like idiosyncratic aspect of like Unix, which is basically file descriptors and how they are used. So every program has three file descriptors open all the time. The first is 0 for standard input, 1 for standard output, and 2 for standard error. So when your program is actually printing to the screen, it's actually just writing to the file descriptor 1. Okay. So when we just close the file descriptor 1, as we are doing here, what we are doing is that the program will still continue to try to write to file descriptor 1, but it's no longer open for writing. So if we run it, we get an error. In case you guys are not able to see, we get an error saying bad file descriptor. This is because we have closed file descriptor 1. Okay. An even more interesting thing happens if we do something like this. So what we're doing is we're just opening a new file with create and read write permissions. Okay. Now the interesting thing is when you're opening a new file, it has to be assigned a new file descriptor. Now we've just closed 1, so 1 is actually available to be assigned to a new file. And what Unix does is it will always assign the smallest available file descriptor to a new file. So here 1 is going to be allocated, assigned to new file. Okay. Because of that, we'll see the interesting effect that everything that ls will be printing will be redirected to this file. Do people understand how that works? Whenever you do printf, it all goes to file descriptor 1. We have closed what was previously file descriptor 1 and we've replaced that with new file. Okay. So without changing any of your printfs, you can have like a million printfs in the program and none of them need to be changed. And with that, let me first remove what previously was there. And then, so now when we run the program, we see that ls has no output. The child is not printing anything, right? But we're also not getting an error. Previously, we got the error saying there's a bad file descriptor. But this time, because we open new file, we are not getting an error. And in fact, if we look at new file, we find that the output of ls has been redirected to the new file. Okay? Do people understand how this works? Okay. So in your project, in order to do piping and redirection of output, you will have to be doing something very similar to this. Okay. There's actually a system call which makes all this stuff much easier for you. So instead of like doing all this stuff like close and then open, remember that this trick of the closing one and then opening another file making and thereby redirecting standard output to that file will only work if that's done in sequence, right? So in order to make sure of what's happening, you can use the dupe2 system call. And what the system call is doing is it's basically saying replace the file descriptor 1 with this FD, with this file descriptor that I'm now giving you. So basically, new file becomes standard output. Okay. So in your program, when you're doing pipe, yes.
That essentially eliminates the need for you to close column one.
Yes. So if you look at what dupe is doing, it's basically doing what we just did. So, but it's a much cleaner way of doing it because you don't have to worry about when anything was closed and what's the lowest available file descriptor. Okay. In your programs, in your project, if you are doing something like piping or redirection of output, you will have to be doing things similar to this. If you want to redirect the output of your program to standard error, or to redirect standard error to a file, or if you want to append to a file, all of that can be done using these system calls. Okay. So if you're stuck on that aspect of the project, this should sort of help you out. Okay. So one question to you guys. So we are doing all of this like closing one and opening new file, right? How is it that we're still able to see some output on screen? Like basically, I shouldn't have done that, but how are we able to see child after 8311 and parent after 8310? Didn't we close standard descriptor 1?
Close descriptor of child, not.
Right. That's an important point. Every process has its own set of file descriptors. So if it's not global. So if you close a particular file descriptor in the child, that doesn't affect anything in the parent. Okay? Any more questions on this? So, I mean, if you don't have questions, I'm going to move ahead to XV6.
And then when a new child is created, then file descriptor 1 is reverted, right? Or it's just created with.
Yes, so when a new process is created, it's always created with like 0, 1, 2 already set for you. So you don't have to worry about that. Okay? Alright, looks good. Let's move on to the next aspect. So we're going to go here. Okay. Alright. So how many people here have used XV6 with GDB? Anyone? Okay, one person. Good. How many people have used GDB at all in connection with anything? Okay. All right. For people who don't know, GDB is the GNU debugger, and it's really useful if you want to figure out like what's going wrong in your program. So normally when you're just using GDB, you can set breakpoints, which means that when your program is running, you can stop at a particular line in your program and inspect state. For example, what are the values of different variables at this point in the program's execution? So it's really useful. It's a tool that you should be getting to know. And you can actually run XV6 in GDB, which is what I'm going to demo now. So let's see. Oh. Okay. 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 So hopefully people already know about QEMU Knox, right? Does everyone know about this? Okay. So if you're running into the problem wherein you don't have the display driver set up, you don't have X, you can use QEMU Knox to run XV6 in your same shell. This has a nasty sort of side effect though. Let me show you. So so here we are actually running the XV6 shell, but the problem is we can't exit. Okay. So what we do is, and I know this is a hack, but this is what we're currently doing, so please bear with it. So we have another terminal open in the same machine. So there we just go and say kill all QEMU. So That's pretty much what we're doing for now to sort of kill QMU. But the advantage of this process, of course, is that you don't need to have X anymore. You can, if you have two terminals open, you can get by rather easily. Okay. All right. So what am I going to show you today? Oh yes, GDB. So quite similar to GDB, to this, you can run GDB in this. Okay. So okay. Okay. Hmm. Oh. Okay. So what just happened was I set up GDB so that XV6 is running within a GDB container, and then from this terminal I just like connected to that so that we can control the execution from here. I'll just run through it again to make sure that you got it. So in one terminal we type make QMU NOx, which is like no X, and then GDB. Yeah. Oh, I'm sorry. Oh, no, okay. So we type make QMU Nox GDB. So what this does is it starts up QMU, but it waits for the connection from GDB. Okay. In the other terminal, which is hopefully much bigger now. In the other terminal, we say GDB. And there are some preconditions to doing this successfully. One, you should be in the directory where you're actually running QMU, make QMU. So both these commands should be run in the same directory, otherwise it won't work. Okay. The other thing is you need to have a file called gdb init set up in your home directory, which basically says that these two commands, which I can send them to you later if you want. But what it's basically saying is, I want to run GDB in this particular folder, and so allow GDB to connect to the instance that is running in that particular folder. We're basically giving permissions on the CSL machines to run GDB and to connect to it. Because by default in CSL, only root can do this. So by doing this, we're actually giving permissions. We're saying it's a safe path in which we can run GDB and connect this way. Okay? So then we come here and then we say GDB. And so what you see here is that, like, when we say continue, then the shell runs in the other QMU. So we can control execution from here. We can actually say very interesting things. So we can say things like break scheduler. Okay. So what this does is every time the scheduler function is called in the binary, the execution will break and allow us to inspect the state of variables. Okay. So let me show you. So what this is saying is that it continued when we have set the breakpoint. So we continued, and then it's called it's once again breaking at scheduler, because if you remember your notes from class, the scheduler is called repeatedly, and I'll explain that in more detail as we go into it. So so this is one way to sort of like inspect what is going on in XV6. Okay. All GDB commands should work.
What is the command?
I don't know off the top of my head. Step into? Is that what you're asking? No?
The next
Step over.
line, I'm saying. To the next line.
So you're broken at some point, and instead of continuing, you just want to go to the next line. Yeah, that's step S will do it for you. Yeah. I can actually show that. So it's continuing, and we're broken at acquire. So this will go to the next line. we can do it like that. Okay. So okay. Let's see. So that's how you run GDB, and it'll be very useful for you. I set it at scheduler, the function. It's in kernel proc.c at this particular line number.
Oh,
So it recognizes the names of functions. So you just have to tell it that's what you want to break on. Yeah?
So when you actually hit a breakpoint, how do you tell it to show you the comments and variable and do all those things?
Oh, so there's a lot of stuff that you can do. Okay. So what it's currently breaking here, and by using L, and I'm asking it to show like what's the code at that point. So you can use that. If you do man GDB, you get a whole list of commands. Basically, you can print anything, any set of variables. I'm not sure like at what point we are here. So what I'm printing here is that the address of variable p here. Okay, so these kind of things are like very useful. Let me see if I can print this. Okay, so now we see that the process that we're currently inspecting in that loop is actually sleeping. So things like these are very useful when you're debugging what's going on with your scheduler. Okay, all right. So let's get back here. Actually, let's get out of GDB because we're not going to be using it for now. Okay. So we're going to just use this thing to kill. And back here, we're just going to do this. Okay. Before that, let me show you some of the code that we're actually running so that what I'm doing makes sense to you. Let's see. So if people remember this function, we talked about this when we were doing a discussion on traps, but this is basically the bootstrapping code for the entire x86. So this is where all your trap handlers and all of the other files, for example, file tables, inode cache, everything else is set up when x86 first boots up. Okay, and from there we actually see that it calls the scheduler. It sets up the first user process and then it calls the scheduler. Now this is the function that's going to be of the most interest to you when you're doing this project. Okay, so let's take a look at what scheduler is doing. Okay, so this is actually the code where we broke when we were doing GDB. So let me see if I can get this a bit bigger. Apparently not. Okay. So the scheduler is like very simple. Like it's only so much code, but it's a little complicated. So I'll be stepping through the code and explaining what's going on to you. So so this is the part of the code that actually runs different user processes. So remember that when we talked in class, we said that when a process gets an interrupt or one process is finished running its time quantum, for example, the kernel will then decide what process to run, right? So that is actually going on right here. So when we are starting this function, what we are seeing is that the first process in the x86 has started up. There's nothing the user has done yet, and then once that's done, this function starts running. Okay, and we see right away that it's an infinite loop, right? So this thing will keep running as long as x86 itself is running. Okay, so the first thing it does is, I mean, it acquires interrupts and some locks, but we don't have to worry too much about that right now. But with this for loop on line 266, what it's doing is it's going to look at all the processes in the system and it's going to check if any of them are runnable, right? If you remember correctly, you can only run a process, user process for example, if it's in state runnable. If it's sleeping or if it's waiting for I/O or whatever, we can't run that process. So it has to be in runnable state. Okay, so that's the first thing that the loop is checking. It's checking if the state of the process is runnable. If it's not runnable, it just continues, which means that it ignores whatever else is in the loop and then goes to the next process in the list. Okay, and because x86 is rather simple, we just have like a very simple array of processes, and we can actually check how many processes there are total. So there can only be 64 different processes in x86. Okay, and the state of all these processes are stored in this particular array p table, and then we just like iterate through this whole array, and then we check the state of all the processes. Okay, clear so far? Okay, all right. So if it's coming to this line, it means that it's found a process that has state runnable, right? Otherwise, we'd just be continuing on and on and on. So once it's done, what it does is it gets it gets a handle to the variable, right? The proc is just a local variable here, and then it sets that proc. It sets a pointer to the current process that we are handling. And switch UVM is actually to make sure that you use the correct stack for this process, right? If you remember correctly, what exactly is a process? It's a bunch of context for one thread of execution, right? So there's all this like register state, there's all these stuff on its stack and things and so forth, right? So when we're running a process, we need to make sure that all of those things are set up correctly before we can go ahead and actually start executing instructions in that particular process. Okay? So, so that's what switch UVM is actually doing. So we can actually jump there quickly and see what's going on. So it's setting up a bunch of like segments. It's setting up a bunch of registers, SS, ESP, for example, and then you should be able to understand at least this line. So what this is saying is that it's setting up the page directory. If you remember in class, there's a page table for each process, and then x86 has two levels of page tables. There's a page directory, right? And CR3 is the register in x86 where you store the address of the page directory. It's sort of the page table based register in x86 architecture. So this particular instruction is saying load this particular address into the CR3 register. Okay. So ignore just ignore the rest of the lines, but at least this line should be sort of like it should make some sense to you. Okay. Questions so far? Okay. Switching back. So here we have switched to the stack of the page tables and other stuff of that process. Then we're setting the state to running. So this is the point at which I've decided that we are going to run this particular process. Okay, and this is the printf that I've put extra here, which basically says we are going to run this particular process, and its name and its PID are getting printed. Okay, and then this is the sort of like crux of the whole thing, which is the switch statement. So right now execution is going on inside the scheduler, right, in kernel context. So what you have to do is you have to move from the kernel context to the user context, and that's done using this particular statement. So what this is saying is save the CPU scheduler context and switch to the process context. The naming is slightly not descriptive because it just says switch without saying anything else. But if you go read like the sort of like code for the function, it says the first argument is old. We save the current register context, whatever we give as the first argument, all of that is saved, and then we load the stuff which is given as the second argument. Okay. So basically, and this is just like a very short assembly line code. If you're interested, you can go read it. We're switching stacks, we're saving the registers, and we're then like loading new registers. Standard fare. But what's important for you to understand is that when you call switch, it's sort of like doing exec in a sense. Okay, so the switch will never return here. Once you call switch, you stop running this particular code, then you switch over to whatever process you are running. So remember how just exec jumps, right? It jumps from one point in the code to the child, sort of magically. And this code also does that very similarly. So once you call switch, the scheduler is not running anymore, it's suspended, and you jump to your user, whatever user process you selected, and that thing is going to run. Okay? So that's like one half of it. How do we go from the scheduler to a user process? Are things clear so far? Yeah? Oh, CPU I think is currently, it's a global variable I believe. Let me see what's defined. So yeah, it's in proc.h. So I think it's a global variable. This is the code, and right now there's no policy. The policy is you look through the array, you find something that's runnable, and then you run it. So this is where you will have to implement the schedulers that you have in project 2. Okay, so right now it's just like first in, first out. Like you keep an array and then you just look through it, and you find something that's runnable, you go ahead and you run it. Okay. Any other questions so far? Okay. So this is one part of it, right? So once we execute the switch statement, we have jumped from kernel code, the scheduler code, into the process code, right? So now we're going to see how do we return from process code back to the scheduler code, because we can't just like leave this hanging, right? So if you remember in class, one of the important hardware support that's required for doing scheduling is that we need a timer interrupt, right? Whatever process is running, periodically we will get a timer interrupt, at which point the process's state will be saved, and then we will trap back into the kernel so that the kernel can take a decision about what to do. Okay, so that stuff is found in trap.c. And trap is another piece of code that you have already looked at. So this part should be very familiar to you, because like, well, technically not familiar, but at least I've explained this in class, somewhat familiar. This is the part of the code that's executing system calls, right? Whenever you trap, because you have a system call into the kernel, this piece of code is what is actually calling the actual system call handling function. Okay? So we sort of like left off when we saw this, and we just like moved from trap, but we're going to go down and we're going to look at the other things in the trap handler. Okay, and here we see there's a bunch of trap handlers. That's the timer interrupt that we are seeing here. There's a lot of stuff like IDE, which is the disk, communication, and all that stuff. Okay. But the thing that's really interesting for you is here. Okay, what it's saying is that there's a process, and the process is running, and then you've got a timer interrupt. Okay, so if this combination of events occur, what we're doing is we're yielding. Whatever process is currently running, it will yield the processor so that it can be scheduled. Okay, so this is how, when we get a timer interrupt, we force any process that's running to yield the CPU and to go from running to runnable. Okay, so let's go see what yield does. So so as we just like described, it's changing the state from running to runnable. The reason it's changing it to runnable is because it hasn't got any IO or anything that it's waiting for, right? It was perfectly fine, it was running along, we just stopped it and we're changing it back to runnable. Only when it's doing disk IO or whatever will we change it to waiting or some other state like that. So it's perfectly valid to be scheduled, so it's in runnable state. Okay, and we are calling shed. Now let's see what this does. So this has a bunch of statements so that it can check whether things are running correctly. When you call panic, basically your entire kernel crashes, and it also has a stack dump so that you can see what went wrong. So it's a mechanism that is used by kernel developers to pinpoint where things are going wrong. When your kernel is panicking, you know that some assumption that you had about your code is now invalid. You may think that at this point this variable should always be 0, but if you put a panic there saying that if it's not 0 panic, you will find out when sometimes it's not 0. Okay, so here we are saying that all of these assumptions should hold. If it doesn't hold, panic saying what went wrong. Okay, but the really interesting part of this whole function is this statement on line 305. So we find that we have the same switch statement again in this code, and if you look at the arguments, it's inverse. Okay, so the first argument is the process context, and the second argument is the scheduler. Okay, so what this particular line will do is it will save the current process context and will load the context for the CPU scheduler and will start running the CPU scheduler. Okay, so the thing about this is there we go. So when the switch statement in the left pane, when 305 executes, it will return to this particular function from where we switched out. If you remember, when we were running a user process, we switched out, so it will come back and it will execute line 278. Okay, so it will say switch KVM as if the switch had just returned from that call. Okay, so we have gone from the scheduler to a user process, and then via the timer interrupt and the yield, we have come back into the scheduler. Does this make sense? There's a lot of jumping around going on, basically because we have different processes and we are jumping from one context to another. So you may be used to code wherein like there's like simple go-tos and like it jumps from one function to another, but in this sort of code, this we sort of jump semi-magically. We say we are going to switch stacks and we're going to switch context, and then execution just magically begins somewhere else. So it takes a little getting used to, because like you have to remember that after line 277 it's going to be running user code, and then when the process yields, when it gets a timer interrupt, it's then going to run line 278. Okay. So so this is how we are actually jumping back from scheduler to user to back to scheduler again. So once it's come back, this will just like run through the loop again. So it's finished running one process. It will go back. It will check if any other process is runnable, and then it will do the same thing over and over again. Okay. So in your code, if you call the scheduler, bad things will happen. Okay, because there's already a scheduler that's running forever and managing scheduling of all the processes. So whatever it is that you're doing, you should edit the scheduler code and do your changes. You shouldn't instantiate another scheduler and do that. Does it make sense? Okay. All right. So one more thing. So let's say that we jump from the process to the scheduler. And the scheduler finds that there's no other process which is runnable. Okay, so it's going to run the same thing again. So where do you think it will continue? The process which we just like stopped, where will execution start for that particular process? If you want a hint, it's on screen. Right. So it will come back here. So when it does the switch statement here in 277, that's going to have the effect of like restarting the user process. And the user process was doing shed before, right? Before it got like switched out. So it will, for the user process, it will seem as if this switch returned, and it will start executing back here. So what that means is that it will go back to schedule, it will finish that, which means it will finish yield, and then it will be as if it's returning from a trap. Remember that we already have all this knowledge about like what to do when you return from a trap, for example, when you finish a system call. So all of that will be in effect. So for the user process, it will be similar to if you just trapped and it came back. Okay, so all the stuff that we already talked about, restoring registers, making sure your stack is okay, making sure your permissions is okay, all of that stuff will automatically be done for it because we're using the same mechanism as a system call. It just traps everywhere. Okay? Any questions? Okay, so let's look at this code actually running. So hopefully that will still easier for you. Okay. So see what's going on here. So we have XV6 starting, and the first process that's running is init code. Okay, that's PID number 1, the mother of all the processes in the system. Okay, so at some point it says it's going to start the shell sh, right? And then you see that it instantiates a new process PID2. Okay, but it still says init. Why does it still say init? Sorry? Correct. Remember that when you use fork, you're actually getting an exact copy of your parent process. So init is in PID1, so when it calls fork in PID2, we're going to be still running the init code. Okay, and at some point later, we find that the exec is occurs, and then it's moved from init to sh. Okay, so we're actually seeing the effect of like exec at one point, fork at one point, and sometime later, after many cycles, we see that exec has happened and init has now become sh. Okay, we can actually see this effect one more time. If we see that we have PID 3. So look at this. So the relationship has just like continued, right? Now we have the shell. The shell is going to exec a new process to run whatever command you're going to give the shell, right? So the shell is process 2. So it's creating a new process, process 3, in which it's going to run ls. So at this point, fork has occurred, and much later, it's become ls, which means that exec has occurred. Okay, and another thing you see here is that we find that the output is all mixed up, right? So if you have any notion of what concurrency is, you remember that we are not getting any locks here, right? We are not printing to the screen in a very orderly manner. All these processes are all printing to screen at the same time. So that's why you're getting things like this. Like one process is, ls is printing its own stuff, and then inside the kernel we're saying we're going to run ls again. So that's interfering with that, and we get all sorts of weird output cases. So if we got a lock every time we print it to screen, for example, we will not get this effect. Okay. Okay. Let's see. So I'm going to show you one more program that's we are going to run. Let's see. So user. Okay. So this is a dummy program. What it's doing is it's basically getting an argument from the user, and then it'll just like do a loop. And for that amount of time. So if we say spin 10, for example, for 10 times it will just do a loop. Okay. The reason we're doing this sort of dummy program is to show you what happens when processes are running at the same time, and we can see how the scheduler is working. So you need to do something like this in your project to show that your spot instances and your reserved instances, for example, are working correctly, right? You want to show that if something is running as a spot instance, it gets a lot of like time. If it's a reserved instance, it gets its chunk of time. If it's spot, if there is time, spot can actually run. So you have to demonstrate all of this in your project. So for that, you'll be writing some dummy programs like this. So programs to just run and it will consume CPU and will show you how they're scheduled. Okay. So let's see how this is running. Okay, so if you see ls, which now is horrible, that's actually spin. Okay, so that's the executable that we just made. And we say, okay, so some things are instructive here. So it says that at this point, it's created the new process, and then we can see that from here exec is starting to give effect because like the new image is running, and then we see that it's going to run spin. That's PID 4. And then we see that once it's done, it says finish spinning. Okay, so your shell has created another file. This has run for like this amount of time. Okay, so this is just like ls, so not much new here. So let's see. Let's have two things running at the same time. Okay, do that. So now I'm having two background processes which are both going to be just like spinning, and then we'll see how the scheduler works with them. Okay. Okay. So it's okay. Okay. So here you see that like when we started the two processes, there's one spin which is PID 11 and there's another spin which is PID 9. And what we're seeing is that the scheduler sees that both of these things are runnable and they're being executed one after the other by the scheduler, right? So a history like this would be like how you convince us that the scheduler actually works. So if you had two instances and one is high priority and one is low priority, for example, you will see in this kind of output that the high priority guy gets a lot more time on the scheduler than the low priority guy. If they get equal time like this, like if they're just alternating like this, then it means that something is wrong. So this is a good way for you to debug whatever policy you come up with and whatever mechanism you use to implement this. Okay, make sense? Any questions so far?
Sorry, but where did you add the one that turned out
Right, it's in kernel. So it's inside the scheduler function that we just saw.
Oh.
So we just looked through this, right? I mean, it's going to do the switch and start running that. So just before that, we add printf saying that we're going to run this particular thing. Okay. Yeah. We had another question. Okay. So no question. Okay. Anything else? Yeah. Oh, okay. So, are you talking about, for example, after switch it should run switch KVM? Are you talking about that? Okay, so that's going to be just in your program counter of your particular process, right? So the way the process normally runs, if you ignore all of these things, is it has a program counter. Like for example, let's say line 74, 274 will have a particular address. So that address will be in the program counter, and then it will have the next address. Once it's done executing that, it'll just like jump to the next address and then start executing that. So as long as you have the program counter, you know what to next to execute. So when we're saving the program context here, process context, we also save the program context. So we know where in the program's execution we are. So it would, I mean, let's say that, for example, that the program counter points to line number, right? So the line number, for example, will say 278. So then when you come back, you know that 278 is the code line that you have to run. So because we're saving that every time we're jumping, when we come back, we know what line to run. Any more questions? Okay, if that's it, you're all free to go. You can come ask me questions if you have any.
Terminal windows.